We are almost done with the inorganic lecture series. This is essentially chapter 13. There'll be about 2 lectures, and the last part is mainly on boranes, which are boron hydrogen containing compounds. Right? Boron is interesting because it can only make 3 sigma bonds and has that empty p orbital, which leads to some very interesting chemistry. And so I like to focus on it. It's not all about boranes. I'm going to talk about borates and other chemicals as well, or structures. And previously we talked about silicates, which are also very interesting and useful compounds. So anyway, this is not a borane. This is one of the elemental forms of boron. It's B12, not vitamin B12. If you Google that, you get vitamin B12. Obviously it's boron. This is the icosahedral form. So this is just boron, and if you look at one of them, each boron is connected to 5 other boron centers here. That's quite interesting here, right? 1, 2, 3, 4, 5. So this is an icosahedron. Of course, we have another form. It's an amorphous powder. It's a beta rhombohedral. The other elemental form. Okay. So boron, of course, is the only nonmetal in group 13. All the others have discrete cations, like aluminum will have a +3 charge, and then once you get down to the lower lying metals, you can have different oxidation states due to the inner pair effect, if you remember. So gallium will be +1 or +3, and the same thing is true for indium and thallium. And so there is actually no discrete boron +3 or boron -5 anion. They don't exist. And so as I said, we already know about BH3, for example. It forms a dimer because in order to get those, it forms those 3 center 2 electron bonds. And then this actually further decomposes and then reorganizes itself to form these borane compounds. So that's kind of what I want to talk about in the process. We have some very useful functions. In fact, you probably used boron as a catalyst or somewhere in an organic synthesis before, if I had to guess. It's present in borosilicate glass. Of course, this is our Pyrex glass. It makes our glasses go resist the change in temperature, so it doesn't crack, right? So if you heat, and all of our glassware that we use in the lab is usually borosilicate glass, so we just call it Pyrex, and so it's doped as the silicate units that are doped with boron, and so there are other types of glasses. Borax, which is also one of the naturally occurring minerals that contain boron, is used as a water softener. It can be a mild pesticide or a cleaner. You know, I've actually killed some fire ants with borax, so it works pretty well, and then it just decomposes, and it's not a harsh pesticide. We looked at boric acid. I'll look at that in a minute to give you the structure again. Let's take a look at a chart of different glasses. I don't really know why I have it here, but just to show you that there are different kinds of glasses that have different. So of course glasses are SiO4. Those are the silicates. We obtain them from sand and melt that down, and then if you dope it with different types of materials, you get different types of glasses, right, that can be useful. And so like lead, which is crystal, we call that crystal glass, and that's usually contains lead. Of course, it's not harmful to drink out of a crystal glass. That lead is tied up between 4 oxygens, and the chances of that leaching from glass is probably really low. I mean, the reason we use glassware in the lab is because glass is pretty damn inert, right? So this comes from a forensic chemistry book, and they actually they grind down these different kinds of glasses, and they measure the density of them, and so they all have different kinds of densities. And you can actually, depending, like if there's a car crash and you know, they leave some glass from either the windshield or from the headlights or something, you can actually test based on the density, do a quick little test and possibly link the manufacturer of that glass that was left there, or the headlight. So there's some really cool forensic. Maybe that's the next series I should record, the forensic chemistry series. But it's a very basic course. Anyway, I'm rambling. So here are the natural sources. I already mentioned the borax. There's ulexite, colomanite, and kernite. There's other natural minerals. Most of them are not too complex, and they each contain these. I mentioned those in the previous lecture for borate and pentaborate and things like that. They all have either tetrahedral BO3, sorry, that's BO4, of course 4 groups would make tetrahedral, or trigonal planar BO3 units, and so that leads to some interesting structures. Okay, so the largest deposit of boron-containing minerals is actually in a town called Boron, California. Okay, so there's a town called Boron, California. It's 1/3 of the world's boron is deposited here in this, so it looks pretty much like a ghost town. And so boron oxygen compounds have a really high energy, and so NASA was interested in mining the boron there and testing it for rocket fuels, but it turned out there were some issues with oxide coating, and so those compounds are highly volatile and they'll explode. So they moved on. But I wanted to show you this. Here's an aerial view of this town, and it's essentially the mine that's here left behind, and they have a NASA museum. But that's about it. That's all the town is, and so you find these minerals here, and these are pretty neat looking, ulexite and colomanite. And so again, they just contain boron, and you still have to extract the boron for the research. Boron is still used frequently here. Here's the structure of borax, and so we looked at that already in a previous lecture. But here we have a trigonal planar center, and then of course it's the tetrahedral centers that also have the charges on them, and so we then need 2 sodium ions, for example, to have sodium borax, and that's also how it exists in nature. We can, so let's just go through a few compounds that contain boron that are interesting, that we've discussed already. So boric acid, of course, is not a proton donor. It actually reacts with its Lewis acid. The lone pair, not the lone pair, the p orbital here is what will act as a Lewis acid, and the lone pair, so hydroxide. So you actually get this BOH4, and then you have the H plus coming off of one of the borons, one of the OH groups, or whatever you want to call it at that point. So that's how boric acid works. Hydroxides, for the most part, are insoluble except for group 1. So aluminum hydroxide is not soluble, but we do know it's amphoteric, so you can add an acid or a base to that, and so that's just in contrast group 13, the drastic difference in reactivity and characteristics. So most of these 3-coordinate or boron-containing compounds that we say are fine, right? We say, oh, BF3 is okay. It's electron deficient, has 6 electrons, but each of these are highly Lewis acidic, and they will react with even weakly coordinating bases and form tetrahedral compounds structures, because it then leads to an octet, 6 electrons on boron versus 8, and that's just the driving force. And so every time we do this, we go from a trigonal planar shape to a tetrahedral shape, and that anion, of course the negative charge, is then located on the boron. Borates are boron oxygen compounds, so allied. This is not just about boranes. There's all kinds of stuff I talk about. You gotta fill up the hour somehow. And they don't go very, very large like silicates. They don't make long chains, and they make just small little clusters. So we have monoborate and diborate, and then we have triborate, and see that already becomes cyclic here. Here I've got, this is the structure, and don't want to discuss this in any great detail. The pentaborane, of course, this is not drawn very well, right? Because you got this one coming towards you, and then this one's going back out because it's tetrahedral. But so pentaborane, and then you can always locate where this charge is by finding the tetrahedral center. So we do need to have a counter ion for this pentaborate. I think I'm going backwards. Let's go forward. It's just kind of a review, I guess, of where you might have seen boron. These are organic transformations that you might have done where boron is used as a catalyst. It can also be used in Friedel-Crafts acylations. We can use it to polymerize. That's actually a pretty nice lab I used to do. We used to take dimethylchlorosilane, right, which is this, CHM, and then these are chloro groups, so you can hydrolyze them to make silanols, so you get silicon oxygen bonds, and they will self-condense, and of course that's a slow process. And when they self-condense, you get siloxanes, which are of course silicones that we use, and that's a pretty important polymer. It's used in sealants that like, you know, silicone rubber boots that are moon boots, or also the silicone that we use for caulking and stuff like that. And so all you have to do is alter this group to alter the characteristic of that polysiloxane. But you can polymerize this by using boric acid. So boric acid will catalyze the self-condensation, speed it up essentially, so that we can get these polysiloxanes. And if I was in charge of the lab, I would have made some polys. And it's like silly putty. You can make it bounce, and it's kind of fun. So give me a call. Get me some dimethyl dichlorosilane. I'll come over to Elms and we'll make some silly putty in the lab. That'll be like finalizing the course and then moving on with our lives. Anyway, so yeah, those are polymerization. Oh, also for alkenes and anyway, you've probably seen boron somewhere. Okay, so back to the diborane, which I've mentioned before. It will, so boron here, BH3 will dimerize, and what makes it interesting is that we have these 3 center 2 electron bonds. So what it is, it's really the sigma bond that does the donation. So it's not a pi bond, or it's really, this bond here is really just 2 electrons, and so they donate into an empty p orbital of the other boron center here, and so we just need to recognize that we have a 3 center 2 electron bond. But that is how boron gets its octet, right? So it has these 3 center, these bridging bonds. It also has terminal bonds, so those are just the regular sigma bonds with 2 electrons, right? So we're going to need to remember what 2 center 2 electron bonds are, and 3 center 2 electron bonds, right? So the only thing left to mention here is that diborane is a gas. It has a boiling point of minus 92.6 degrees Celsius, and that it will further decompose and then rearrange to make other clusters. So here are 3 useful reactions of diborane. You can hydrolyze it to make boric acid, and we know boric acid has some good functionality. We can also do a pyrolysis, basically burning diborane to make borate, and so borates are also industrially used compounds, and like borax, right, is that, and then we can reduce boron here. Like if you look at diborane and you assign oxidation states, if this is a +1 and then this has to be a -3, and so this can be further reduced with lithium hydride. Remember that lithium hydride, IDE, is an anion, so the hydrogen is oxidized. Here's going to have a +1, and it's the boron that's going to go to -5, so it's further reduced in this case. Interestingly enough, we use this lithium hydride is a reducing agent, but so is lithium tetrahydroborane. So this is no longer a hydride, but it's still used as a reducing agent, of course, in carbon containing compounds. So those are just 3 examples of where diborane can be used industrially. Here's the synthesis of diborane. We can do this in the lab. In fact, I've done this in the lab. It's pretty simple. You can buy sodium tetrahydroborate. Commercially, iodine, you just add iodine and you generate diborane. All right, again, this is a gas. Let's write this down, minus 92 degrees Celsius roughly. And then the other gas you produce, of course, that's a solid. This will stay behind. Like if we generate this in a flask, for example, and if we were to hook it up to a gas system, which I'll show you in a second, if you add just some iodine, you generate diborane, so you're going to get the gas H2 as well as B2H6 that's going to come off. And so we somehow have to trap these two gases and then separate them from each other, and so they have drastically different boiling points. Hydrogen gas is minus 253, so then we just need to find something that will trap that, and so carbon disulfide slush bath. So if you take dry ice and carbon disulfide, you end up with a temperature of minus 110 degrees Celsius, which means you are going to liquefy the diborane, and the hydrogen gas will go right through it. And I'll show you here in a sec how this works. This is how it's done industrially. And so anyway, these are just 3 different processes of how to make diborane. This is a standard Schlenk line or vacuum line. In case you haven't seen it, I'll go through it quickly. If you know, skip the next 2 minutes, I guess. All right, so we have dual manifolds. There are better pictures. One is hooked up to an inert gas atmosphere. Argon or cheaper dinitrogen is usually sufficient. And so we have a gas, inert gas atmosphere in one manifold, and then we hook the other manifold up to a very strong vacuum pump, and then we usually put a liquid nitrogen trap here to so that your pump doesn't get destroyed, right? If you suck in all of the organic solvents that you might want to remove from a reaction, and you can ruin the pump. So we usually try to trap everything in liquid nitrogen, and so then there are these two-way valves that you can either connect to your system. You're going to hook up your reaction vessel here, and you can hook it up to vacuum, or you can expose it to an inert gas atmosphere. And this is how we do air-free chemistry. There are better pictures than that, but so if we are to do the diborane reaction, what we would do is we would have, okay, so my art's gonna really suck, but so here we do have we're gonna generate the two gases. We're gonna hook this up to our vacuum line. We have our manifold here. We have our liquid nitrogen trap here. Of course, hydrogen will go right through even the liquid nitrogen trap. So, but what we can do is we can shut this off. We have a static vacuum then, right? You don't want to refill this system, but so you're going to have all of this open, and then you hook up a U-trap to your system, okay? So you will trap your gas with a CS2 slush bath, right? So this is dry ice. Of course, dry ice is carbon dioxide. It actually has a melting point of, or it sublimes at like negative 72 or so. But combined with the carbon dioxide, you get down to minus 110. So what you do is this all gets trapped in here. All of your B2H6 will be trapped in this U-trap. And then what you do is you keep it in there, you evacuate your line, and then you hook up a fresh flask, and then you remove this trap so that the gas can go back into a vessel, and then you can seal that off, and then you have your gas, and then you can do a GCMS. And we used to do this in the lab. We used to then run a GCMS on that, as well as UV-Vis. And you can do that for germane or for diborane, and so those are some kind of fun labs that you should be doing in inorganic chemistry lab, right? Okay, this looks great. If I snip this, nobody would know what the hell. But anyway, so this is kind of the transition to the boranes. The last part is just looking at boranes and what happens. So this will then decompose, and you can then and I'll stop right here and I'll come back to that. And so and this can make, you can have like B6, H18, things like that. We have these types of compounds, and so they all have different structures, and I'll show you a method called the Sticks rules, and I'll go through those, and that's the last thing we're going to do, and then maybe look at some other cool stuff if I have the energy, but I don't have the energy anymore. So see you in a few. It's another 20-minute lecture and we are done.